Okay, sorry. Front end VLSI. Okay, sorry. Front end. Okay. Okay, sorry. Front end VLSI. Okay, sorry. So let us continue. This is going to be, it's sort of a large diagram in the book. So I will try to um, describe some of those steps, and it's not so important to go through the diagram like exactly how it is in the book, but we will look at the main steps. So we look at some of the steps before, so obviously those we will ignore. Okay, so first is, of course, we always start with a specification. We already, okay, so we have added this one step here, which is your RTL verification. And this is traditionally done using your test bench. That is, you are writing some Verilog code and you write another file called as a test bench. And in that test bench, you instantiate this design and you give it different inputs in random order or different this thing in any order you want, but that particular step is called as RTL verification. And once this is done, okay, and you're sure it is correct, now we go for the RTL synthesis. And how do you do RTL synthesis? This is the question. And of course, we are not going into too much detail, but I'm sure you are curious, right? I am writing something like if then else. I am writing that is not representing any known gate, a statement, for example, assign statement. Okay, how does that get converted into a gate level description? And RTL synthesis is generally the most common way to do RTL synthesis is to have a rule book. Okay, this rule book is something like a lookup table. For example, select. If you have select in your Verilog code, okay, that typically translates to a mux multiplexer. Okay, and if you have some other thing like logical expression, logical expressions and or not, etc. We have only logical expressions that are for the gates. So automatically there is a mapping. We don't have to do much work. Logical expressions, whenever you have, you can look at gates. And similarly, okay, non-blocking statements. These rules are more top level rather than directly translational. But when you have non-blocking statements in your design, generally that means that you are designing a sequential logic. When you're having blocking statements, that generally means that you are designing combinational logic. So this is a large set of rules. Okay, so based on these rules, whenever some statement comes in the Verilog code, in the RTL code, you can directly translate that into a gate level description using these tools. So that is the main this thing in RTL synthesis. Of course, there is some, I wouldn't call it intelligence, but there is some amount of optimization also based on some structural checks, based on some other steps, etc. But at the end of this RTL, we have transformed. This is what is the thing that I was saying there also. We have transformed the code into a gate level netlist. And gate level netlist, before we do anything, okay, one very important step is called as logic optimization, and you have already done this. If you have ever used the K-map to simplify a logic expression, that is an example of logic optimization. There are many more higher levels of logic optimization also. One level higher than K-map, if you have, for example, 5 terms in the expression, then there is something called as Quine-McCluskey method, and there are other commercial logic optimization tools also. Many of them are open source. If you search, you will find them. But basically what happens here is, input is also a gate level description, gate level netlist. Output is also a gate level netlist. But reduces the gate level expressions. It doesn't transform the code, okay? It's from gate level to gate level only. But what it does is, it reduces the gate level description, so that if I can, suppose I have some function, in this stage I have the gate level netlist, but it has some 25 terms in it. Suppose I can reduce that to a function with just say 18 terms, because the other terms were either redundant or they were in such a way that they are never coming into the picture, etc., etc. All those are made into a optimized form at the end of this stage. So this is the final gate level description. Okay, and still we are not done. This is not the end of front end design, because we are going to go into a little bit more complication, in particular at this stage. Okay, so we saw this RTL verification here. Okay, when we have a gate level description, that is a netlist, we generally call it a simulator, because it's no longer in terms of variables. Here all your design is in terms of variables. Okay, we have no concept of registers, we have no concept of memory, we have no concept of logic, definitely. So we call it as verification using a test bench. But once we are in this stage, okay, now all our variables are binary, 0 or 1. So whenever we are working with that, we can work with a simulator, and this is the same as this. A simulator, it takes the input, okay, and you give it different, it takes the design, you give it different inputs, it produces the output, and based on your original specification, you have to verify if the output is correct or not. That is the traditional. This is the newer. Okay, formal verification is something that is, again, maybe I mentioned this earlier also, but formal verification is something that is still in the research domain largely, but it is possible to do for small blocks. Maybe you have some very important this thing where you have to absolutely verify everything. Okay, so for example, okay, 1000 gates, relatively small, not so big, and this can be done using the simulator. But the problem is, are you guaranteeing me that every possible input combination you have given? That is not possible to do, because even if you have 1000 gates, okay, you might have 32-bit, you might have 64-bit, giving all the possible input combinations, because you're saying 64-bit, okay, which means that you have maybe 2 power 64 different inputs at the minimum. And then if you go inside the circuit, because you're giving the inputs at the primary inputs, it has to go from the input to the output. Okay, and when you're looking at the internals of the circuit, maybe not all these 2 power 64 are coming in the same order, they might get transformed. So then the question comes, what about the order? If after this input I give this input, will the circuit malfunction? So questions like these, okay, it's very difficult to answer with simulation. Generally, they won't cause a problem. So if you have an ordinary block, or if you have something that is not so critical, okay, you can live with it. Even if it causes the problem, it might get overshadowed by some other computation or some other thing. But if you have something, okay, that is at the heart of your design, and in that case, formal verification is better, because formal verification, formal verification doesn't mean that we do the same thing but we do simulation inside. Okay, there is no question of simulation, there are no inputs at all. Formal verification doesn't care about the inputs to the circuit, it only takes the design, okay, and then it checks for all possible combinations. This is the whole idea. It checks for all possible combinations through different methods. One example is Boolean satisfiability. What is the meaning of this satisfiability? It's a very important problem in theoretical computer science. Okay, not Saturday, satisfiability problem. And what it does is, it asks questions about the state of different parts of the circuit. So for example, I have a block here. Okay, this is my 1000 gate block, and suppose I am giving this to some other block, and if, for example, the output 1010 is an error, okay, now the simulation, the problem is, I don't know which input combinations will produce this error. So I can try 1000 inputs, okay, and if 1010 is not coming, then I can say, okay, as far as these inputs are concerned, the circuit looks okay, let's go to the next step. But the problem is, I have given only 1000 inputs. It might be requiring 1050, or if I come to 1075, I might be generating this error, and that might be much larger also. That is the main problem with simulation. In formal verification, okay, we can ask a question like this to the solver. It's called as a satisfiability solver. Does this block, given this netlist, okay, satisfy output equal to 1010? Just tell me yes or no. I don't care about the input combinations. Okay. If this block is satisfying 1010 and the solver gives yes, that means that there is some input combination. Maybe you can get that input combination. So, but there is some input combination which is producing this output 1010. There is a problem. Okay, that is the main advantage of formal verification. We can ask questions like this to the solver, and this only works with Boolean because the 1000 gates are there, and the 1000 gates inputs and outputs can have only two values. So if you have 25 gates, for example, you can sit for maybe 1 week and work out all the possible combinations. That would be simulation. Okay. Formal verification uses completely different algorithms, mainly something called as Boolean satisfiability. Based on these algorithms, without doing a simulation, it can verify statements like these for us. And we cannot do this for the full block because it will take prohibitively large amount of time. Okay, even for 1000 gate block, if you want to do formal satisfaction, formal verification, sorry, formal verification for this might take a few hours. Okay, so as the number of gates increases, the time increases exponentially. So if you have 10,000, from a few hours it might take a few weeks. And if you go to 1 lakh gates, which is the typical design in modern systems, not the overall design, okay, some particular block given to one engineer might be 1 lakh gates. For 1 lakh gates to do a formal verification is not easy at all. It might take you a month at least if you have to do it. If you're at the final stage, if you're just ready for tape out, right? We mentioned tape out earlier. If you're just ready for tape out and you want to be absolutely sure that this has to work under any circumstances, maybe then they will go for formal verification. But once that increases more and more for the full chip, for example, if you have 10 lakh or even 100 lakh gates, no chance of doing formal verification. But formal verification is one of the most important parts of the verification step. And another interesting aspect of this whole VLSI design, we see these checks a lot, right? And I said that the checks are when some error is happening, so it may require some manual intervention. In the overall VLSI design flow, okay, 70% of the time is going for the verification steps. So if you see after every design step, there is a verification step: RTL design, RTL verification, gate level netlist, logic optimization, then simulator or formal verification. Similarly, in every step, there will be a verification step. So in the overall design flow, 70% of my time, okay, is going for verification. Only 30% is the actual design step. So this is one of the reasons why we can guarantee that the final output will be error free. We are continuously checking, rechecking, checking every time there is a transformation. That is another aspect of this checking. Why is it enough that you check it here, and why do you have to keep checking it every time? The reason is the design is continuously getting transformed, and if something, of course, the tools, as far as possible, they will try to maintain the functionality, but because these designs are so large, something could happen that the functionality is misunderstood, the functionality is lost. So that is why it's important to check it after every transformation. And the verification is the majority of the time, 70% of the time in VLSI design flow goes for these verification steps. Okay, so after this, we are sure that the logic is fine. We have a gate level netlist. Okay, next is another very important step, and we're going to see a few new terms here also. So I'll just redraw on top of this so I have a space there. So this step, we have mentioned it in the slide also, but it's very important because the netlist, okay, is consisting of logic functions, that's fine, but not all logic functions are part of the library. Now, library is the key word here. We have a finite set of gates for which we want to produce the final netlist. Okay, we don't want to have any other gates as part of our netlist. So how do I do that conversion? That is what this library mapping does. It converts the gate level netlist that we got, okay, into a different gate level netlist, but now everything is in terms of our library, and this is the keyword, okay. This library is very important for us because we don't have access to all sorts of gates. So for example, at the gate level netlist might have produced something like a 5 input AND gate, okay, but 5 input AND gate might not be part of my library, and I want to produce a design that only consists of gates or cells, both are the same, from my library. So we have to produce that transformation. So for example, this might be very simple conversion. For example, 2 input and 3 input are there in my library. So instead of one 5 input AND function, I will see my library, what other gates are there, okay, and try to transform 5 input into available gates. That is the mapping, and again, completely based on software tools. We cannot do this without the software tools, but this is very important because at the end of this step, okay, we have same thing. This is again gate level netlist. So we can have simulation or formal verification. Okay. And here for the first time, we can do timing analysis. We have never done this before because we didn't have any timing information. When you look at a gate, AND gate, OR gate, you only know the functionality. If you're looking at simulation or formal verification, it is only working at the functionality level. What are the values of the inputs? What are the values of the outputs? How fast is the output being produced? We have never done that analysis. We couldn't do it, okay, because we didn't have that information. How can we do it now? It's because of this library. Timing, area, and power. So these are the things that are also available as part of the library data. It's not just the functionality, it's not just the gate, it's not just the 2 input gate or the 3 input AND gate. It is also the timing, power, and area information of each of these cells is also done. That is somebody, some engineer has sat and done this. So this is also, I know a few people who are doing this type of work also because suddenly they have a new customer. For example, in automotive, okay, they want some type of integrated circuit. So somebody is creating a library cell so that every time a new integrated circuit is required by some automotive industry, okay, they can use this data. That is, the engineer is sitting, he is drawing the layout, he is performing the simulation, and he is generating these 3 numbers for that particular layout. And all those together will form part of the library data. Library data is nothing but a text file, okay. It will have the name of the gate. So for example, this might be and 2, okay. It will have the area of the cell, it will have the timing information, it will have the power information, and this is all written inside a text file, and that is the library data. And once we have the library mapping and this, we can do a timing analysis for the first time. Okay, and again, if it is not satisfied, we have to go back. Okay, what is the meaning of go back? This is the way where we are trying to maybe change the mapping. Okay, so here, for example, take this example itself, and 2, okay, is one cell that is there in the library. We have used this in our mapping, and unfortunately the simulator is okay, formal verification also okay, but let me add this also, but the timing analysis is giving me a problem. So I might go from and to Excel extra large. Okay, and as we will see in the third or fourth unit when we are talking more about time, if we make the size of the gate bigger, it becomes faster. Okay, why? We will see more detail in the third or fourth unit. But this is why for the same functionality, the library might have anything as much as 4 to 8 cells. That is for 2 input AND gate itself. They might have 4 to 8 varieties of 2 input AND gate with different sizes. And it might try with one size. Okay, the functionality will always be satisfied because always the functionality is the base requirement. But the timing might not be satisfied with one cell. Then what will it do? It will replace it with the next higher cell, and it will keep going up. Of course, after a certain point, if you're not able to do it, for example, it might go all the way up to or inverters, for example, inverters 4, inverters 4XL, etc., etc. Many are there, but at a certain point, it might fail. Of course, there's always this thing that timing might not be satisfied, but we cannot do anything about that. But there are multiple cells for each functionality, and it will try. If it is satisfied, it will go. Otherwise, it will redo the mapping with a new cell, and it will try to satisfy the timing. So once the timing analysis is done in this step, okay, so once that is done, then we are almost done with the front end. So up to this particular point is your front end VLSI design, and the test logic is very important. Take a few this thing, because test logic is something that is very particular to VLSI design. Okay, it's not very intuitive, meaning that I have a gate, okay, and if I want to test that gate, I want to be able to give certain input patterns to the gate. But the problem is the gate might be somewhere deep inside my circuit. So somehow, let's say that somehow after the fabrication, okay, so generally when you go for fabrication, we said that there is a step called tape out. Okay, so when tape out happens, then you don't have to worry. Generally, tape out, at the end of tape out, there's a party, because the few months before tape out would have been really hectic. People would have been working day and night, no weekend, nothing. They might home at 4 o'clock, but even when they come home, they are working. And when that tape out happens, that means that it's gone. You can wait for a few months before the first silicon. Okay, that is, they are not going to manufacture it yet. They have manufactured it, but they are giving you a few prototypes of the manufactured silicon, and this might take a few months before it comes back. But that is called as first silicon. Okay, and in that first silicon, now the test logic is already inserted. We are not inserting it now. During the design phase itself, okay, we are having this netlist. This is going for physical synthesis. Back-end design happens, tape out happens, and it comes back to me. That is the first actual silicon implementation of my design. And now this comes into the picture. It's not gone to the end user. It's still with me, the designer. Okay. And what is the meaning of this test logic is every gate, okay, in the design can operate in normal mode or in test mode. And there will be a pin as part of the inputs to decide whether the gate is operating in normal mode or test mode. And if it is in test mode, that means that the inputs of the gate are coming from a different source. Where is it coming from? That is this test logic. So these are all special registers, for example. They could be special logic also sometimes. But generally, these are different set of inputs which are easily accessible. Okay, these are not the primary inputs. These are easily accessible, and through these, I will feed whatever pattern I want. Okay, I cannot do that otherwise. Suppose it's operating in normal mode, and my gate is somewhere deep inside the circuit. Primary input I can give 1010, but for my gate input, suppose I want some particular pattern, say 100. How do I give that? I cannot. It's very difficult for me to retrace. Okay, because there might be hundreds of stages before I reach my gate. So this test logic comes into the picture. I can test it with whatever values I want. And what is the reason for giving it particular values is certain types of fabrication errors. This is the main problem with the VLSI errors in the VLSI design after fabrication. That is, now we are talking about post silicon, what is called as post silicon verification. Obviously, some new things that are there in terms of timing we can do again. Okay, but in post silicon verification, one very important thing is, are some particular gates, okay, or some part of the circuit, am I having some fabrication error? We want to correct that also, because now I'm having the actual silicon implementation. Okay, how do I check that? I can give some input. I know what is the output to expect because I know the gate functionality. But I should be able to give that input, and I do that through the test logic. And test logic, generally, like I said, there is a test mode and a normal mode. When the first silicon comes, at the design team itself, they have large equipment, something like we don't have anything in this room, but you imagine something like a fridge, something as big as a fridge. Okay, you keep your IC inside that, and that has a lot of complicated signal generators. It has a lot of analog signal generators. It has a lot of digital pattern generators, and it has a lot of hardware circuitry by itself. And it will test that circuit by putting it in test mode, and that might take a few days by itself. Okay, and once all that is done, then you know that finally the fabrication errors are also not there. After that, you can go for mass production. Until that, they don't go for mass production. But this is the key point for post silicon. After the actual silicon is there, there are many things that they check, but one of the most important things is test for fabrication errors. And that is also inserted as part of the front end VLSI design, because these are also logic gates. Anytime you're putting logic gates, you have to put the test logic also. Okay, and then you get a new netlist. And generally, we don't do simulation after this because, like I said, that's a different mode of operation. Test and normal mode will never mix. Okay, suppose you're buying a IC today, you cannot put it in test mode because before it's given to you, that pin will be disabled. They will not remove all this. It's impossible to remove it. It's part of the network. It's part of the IC. Okay, but just that test mode pin will be disabled. It's not a pin that the end user can use. And once all this is put inside the integrated circuit, this onwards is my back end VLSI design. Okay, so this part is bottom part, and most of these are explained. Just timing analysis, I think I mentioned this briefly, but there is one very important tool or algorithm, call it what you want, which is called as static timing analysis. And this is similar to the formal verification that we talked about, where we don't give multiple inputs and see if the circuit is functioning. Here also, okay, generally when you want to verify timing, you might give some input, you might see the output and see, okay, how much time is it taking for the output to be produced? That is my delay. But here it does something completely different, okay, based on okay, so some sort of structural analysis of the circuit is being performed during static timing analysis. And what that means is I have a circuit, many inputs, many outputs, okay, and there can be many paths. Each of these inputs, okay, somehow they're having an effect on the output. If it's having no effect, then I can remove the input. I don't need to keep that there. But I can have these types of connections where, for example, okay, there are many ways between the input and output. So this is one path, this is another path, like that. In this diagram, I don't have any other colored chalk, but if you see closely, there are four paths, okay. Which of these is the critical path? The paths will be identified by the static timing analysis tool, and it also has to identify which is the critical path. That is the easy task, okay. The path along which the delay is maximum, so every path has one or more gates, okay. Here there are 1, 2, 3 gates, here there are 2 gates, here there is 1 gate each. Now these 2 gates is a XOR gate and AND gate. Here is a NAND inverter and AND. So even though there are 3 gates here, this and this gate are expensive. XOR gate is little more expensive in terms of delay. So the tool has to decide which path, okay, it cannot just directly count the gates and say 10 gates, okay, maximum. It has to see the library information and decide which of these has the maximum delay. It might be this path along the XOR and the AND. That depends on the timing analysis and the library data timing information, okay, and based on that it will decide that one particular path the delay is maximum. That is also called as the critical path, okay, and the delay along that critical path is going to be the maximum delay for that particular design. So any design So for example, if this path, the delay is 5 nanoseconds. This path, the delay is 8 nanoseconds. This one, it is 4 nanoseconds. Here also it is 4 nanoseconds. Okay. The critical path is the one for which it is 8 nanoseconds. That means that for this design, to produce the output, what is the maximum amount possible? That is 8 nanoseconds, which is determined by the critical path. So this type of analysis doesn't involve inputs. We are not giving any inputs. Okay, we are just looking at the structure of the circuit, and based on that we are making the decision by identifying the critical path. So this type of analysis is very important. Again, we will do it once the library mapping is done. We can do this thing. So we will also see this during the lab, if whenever we do that. So this is one very important part, which is called as timing analysis. So one more thing I didn't mention, power analysis. Okay, so power analysis is also an important aspect, since we have the power information as part of the library data. We can do a power analysis. It's not very distinct, just what it says. Okay, it's just the analysis of average. This is not anything high tech. We have the netlist, and based on the library data for each cell or for each gate, we have the power information. Just add it. Okay, add it for the old design. But more importantly, that number is very important for many reasons. Okay, one reason is obviously the specification. The specification might mention a power consumption specification also. Okay, but the higher, the more important reason is, even if it doesn't mention, most devices today are dependent on a battery. Okay, my mic depends on a battery. I have charged it, it has a battery, it has a certain life. Similarly, your laptop, okay, if you're not charging it, then you need a battery. Your mobile phone definitely needs a battery. So most of the devices today require, okay, low amounts of power consumption. That is why we need to measure that. And many times, if by something the power consumption is low, that also becomes an advertising point when you're looking at an overall product, when you're looking at advertising this thing for a product. If you say that low power consumption, then that's a catchphrase today, because maybe it's not so fast, but if something lasts me 1 day for sure without having to recharge or anything, that's very important. So today power analysis is becoming more and more important. There are many alternate ways to design circuits. We will see maybe one or two methods during the course, but the target is not the speed. Okay, sometimes the target is power consumption, and that's why we need to measure the overall power analysis for the circuit also. And we can just briefly summarize. Okay, so one single goal, if I can say, what is the goal of this type of flow? Okay, the one single goal is there should be no errors. Now, we don't want to get confused between this test logic insertion. This is a completely different aspect that we are checking. That is checking for errors that are induced by the fabrication process. Fabrication process is also not perfect. Okay, there might be some errors there, But in this flow, we are not looking at that. Okay, we are looking at functionality, timing, power of the final netlist. Up to this point, whatever I have, is it perfect? Okay, that's all that I am looking for. I'm not looking for anything more than that. And the single most important objective of this particular flow, okay, and what is the tool or what is the steps in the flow that aid this? That is the steps that aid in that are the verification tasks. Every step when we transform, we are doing a verification. We are doing a checking. If possible, when we are at the gate level, we are also doing formal verification. Okay. So these steps are the ones that are ensuring the error-free IC design, because IC cannot be repaired. Okay, if there are very few stories of integrated circuits having errors, but it's not unheard of. Even our great Intel, okay, they had an error in the arithmetic processing unit. Maybe around, it was quite popular around 2015 or maybe earlier. If you search for it, you can find it. But it was happening that it was actually invented, not invented, sorry. The error itself was, I think, discovered by a mathematician when he was performing some sort of very obscure or very what can I say, a very complicated calculation maybe, but he was getting that error again and again. And when he went back and he went back to the sales team and it went back to the design team and it went beyond that also, they actually found out that in some extreme cases, okay, the circuit, the microprocessor, their core product was actually malfunctioning, and that cannot be repaired. Okay, it produces two things. One is obviously people are going to be a little bit more cautious before they buy your product again, because those are big stories. Whenever they come out, they are very big stories. And the second effect is you are going to lose revenue because of that, but also as a responsibility you have to replace the product. So many mechanical companies, we hear this much more often. Many vehicles, Maruti, Toyota, they are recalled, okay, because they have discovered some defect. And fortunately there it's a simpler procedure. You can go to the manufacturer, they can replace only that particular, maybe it's a seat belt. This happens pretty often. Maybe it's something related to some other mechanical part. You can replace only that part, but you cannot do that for integrated circuits. Okay, you cannot replace that gate and say, okay, thank you very much, but here's your new IC. You have to replace the full IC, and that is the reason why this thing, in summary, okay, this whole thing is targeted at error-free operation. And how does that happen? It is dominated by verification tasks. So we'll stop here now. In the next class, we will be looking at the physical synthesis part. We stopped here, okay? And there are many steps that happen after this, which we call as physical synthesis. So we will see in the textbook, it is called as automated layout generation, but it's also physical synthesis or physical design as we call it here. So we'll see what are the steps that go through in physical synthesis, taking the netlist, okay, gates, and transforming them into the layout. So we will stop here and we'll continue on the next class. Okay, thank you.